Okay, in this example we design the PID. Okay, first of all we need to give the hold condition given system of figure at the right hand side. Design a PID controller so that the system operates with a peak time that is 2/3, which means that 2 divided by 3 that of uncompensated system at 20% overshoot with 0 SS error. Okay, the R system is just like this one, plus minus the CS and K S plus 8 S plus 3 S plus 6 S plus 10. Okay. Plus 10. These are GS. Okay, so we have 1 condition, 2 condition and 3 condition. Okay, and the solution, how can we do that? First of all, we need to write step 1. For 20% overshoot we use the formula just like this one, zeta minus ln percentage os divided by 100 and square roots of the pi square log square percentage os divided by 100. Okay, we need to find it for the zeta, but how can we do that? And so the return to the MATLAB code in here, and this is the ver6 code, PID design effect. Okay, so we deleted the whole terms in here just like this one. First of all, the unity feedback system should be given in here, the PID design. Okay, this is what the P design. So -8 it's our zeros, and -3, -6 and -10. Okay, and the gain is 1. That's the P value, zeros, poles, gain, and also the percentage overshoot must be equal to the 20. Okay, and so if I run this code, we have the 0.4559, right? And so we need to write that in these terms, the zeta 4, 5, 6. Okay, we must use this thing in here. Secondly, now we can find the dominant pole at root locus, right? Which is equals to the what? We should draw the root locus of these terms. Okay, the figure are locus GP and title root locus of uncompensated system. Okay, and S grid zeta must be given in here. Okay, and so if I run this code and then I'm sorry. We have this root locus. Okay, and so we need to select this point in here, just like this one. And so we need to find this value in here. It's the 20% of these terms for the what 20% overshoot in here. This is what are terms. Okay, so what's the basic dominant pole in here? The dominant pole is equals to what? The minus 542 plus 10.6. Okay, but in regional information, minus 5, I'm sorry, in precise calculation gives us minus 5.415 minus 5 j 1057. Okay, this is the exact value of this graph. I couldn't write the code of these terms because in the first lesson we will derive the what, the damp and the closed transfer function for the PID controller to find it automatically in the method way. If you are using the this code, and then you will reach this value, but this is also closing this value, minus 542 10.6. okay, this is the what, this is the rounded value of these terms. Okay, and so what's the gain of these terms? Our proper P gain is equals to what, to 121.5. okay, this is the exact value of this overshoot, just remember that. But in the graph we have the 122, right? So these are the codes for these graphs. So using the peak formulation in here, TP from root locus, which is equals to the what, the TP 0.297. This is the simple representation of the what, the R peak formulation coming from the second order system. You can calculate it. Okay, but see, these are the nomination of this code. You understand that our proper peak formulation coming from the what, the second order representation, and then we can find these calculation values of these terms. Okay, and so in the second step, before going to what, the feedback system, we must write also the selected KP 121.5 CLTFP feedback can be called in here selected KP times GP unit feedback 1 and figure the step signal CLTFP 1.5. It's the second. Okay, and so if I run this code, and then we will have this properties. The peak response is at the what, 20.7. okay, and so this is not the what, the second order system, this is the third order or fourth order system, and so it may have the different overshoot value in here, just remember that. And also the T peak time is equals to what, the 0.3, right? and so which is coming from the what? These terms. And so the TP can be found with the what? With the root locus, and then we will have these values in here. And so the question asks about that the 2/3 time of the uncompensated system. And so at the second step, step 2, the new TP must be found by with the what? TP new is equals to what? The 0.297 times 2.2 divided by 3. Okay, and so just remember that roots are S1 and 2 minus zeta omega n minus plus omega n zeta square minus. Okay, and so this the VD, damped natural frequency, right? And so just remember the formulation of the what? The TP. The TP can be calculated with what? The pi divided by omega d in the second order representation. And so the VD can be found with what? The pi divided by TP, right? These are the basic formulation for calculation of the VD. Okay, and so the VD can be calculated with what? The pi 2 divided by 3 times 0.297, just like this one. And so we have the 1578 value at the damped frequency of response. Okay, and so how we can formulate these coefficients in here, just like this one. First of all, we have the zeta and the omega n values in here, right? And then we can draw the root locus, sigma j w, right? And so what's our dominant pole in here? The sigma must be equal to 5, 1, 4, 5, and so the pole desired is equals to what? The 5, 1, 4, 5. This equalizing or the confirms or satisfies for the what? For the overshoot values, and then plus we need to write the what? The 1578, right? These are the new pole to be calculated in here. But in the previous case, we have the pole at the gain of the 121.5. We have this region, but we must set the new pole in the PD designs in here, just like this one. And so in the root locus techniques, we can write the what? The poles in here. This is the open loop poles, and also we have this kind of information. This is the line of the zeta 0.456, and so we have the points in here, the k 121.5 and minus 5 145 plus j 1057 is the previous pole in here, just like this one. And so also we know that from the geometry 117.13 degrees in here, and then the sigma must be contained with what? The VD, tangential information of the what? This term. This is coming from the what? The geometry of the R location, right? And this must be equals to what? These terms minus 8.13, right? Because we need to what? We need to provide this information, but this must be updated right now. And so S new should be equalized with what? The minus 813 plus minus j 1578, right? But remember that the zeta should be selected as this one. And so how can we change the real part of this term? updating the omega n frequency values in here, just like this one. Okay? And so we need to add the some zeros to change the transient response of the R study, right? We need to add a 0, right? The TP must be changed in here. And so if I draw the root locus in here, just like this one, j omega, and so this is the 1578, and also our new transient response pole must be given in here. And so if we want to do that, we need to add the some closed loop zeros, theta 0 compensator in here. This is the new 0. To what? To set the new transient response in here. And so the total angle is the what? The minus 198.37 degrees in here. Because we have the 3 poles at the open loop system, and also we have the what? The 1 zeros, and then we can collect the whole terms in here, theta 1, theta 2, and theta 3. Just remember that this question. We have plus 3, plus 6, and plus 10, and we have 1 zeros in here, and also theta 4 zeros, and we need to add the 0 compensator must be equal to what? The 180 degrees. And so the 198.37 minus 118 is the equals to what? The this degree, 18 degrees. Okay? And so this must be equal to the what? The 18.73 degree. Okay? And so just using the geometry of these terms, we will have 1587 z c minus 813 must be equals to what? The tangential information of the 18.16, because this information is the what? The 15 value, which is the what? The 0 closed loop pole minus 8.13 must be calculated from this one. And so from this nomination, ZC must be equals to what? The 5592. Okay? So therefore GPD S must be equalized with what? The S plus 5592. Okay? So how we can show this code in the MATLAB? First of all, this is our bit basic diagram, but the second is related to what? The PD design. Okay? In the PD design, we need to take these values in here. This is the PD and PD and PD. And so minus 8 and minus 55.92 must be added in here, because this is the PD, right? And so we find it from the root locus, right? From the geometry, to provide the desired roots in here. And after that, the PD is given in here, and figure must be updated with what? The GPD, right? Like this one, GPD. And so this must be commented in here. GPD, this is the compensated system. What? But PD, compensated system. And so if I run this code, and then we have some error in here. We don't have the zeta values in here. I'm sorry, guys. So we need to take these values also. Okay. to draw the zeta line. And so if I run this code, and then we will have this nomination for the PD selection in here. So we have the 2 points in here, just like this one. For example, we can select these terms in here, and then the intersection point must be selected in here. 5.34. It's the overshoot in here, and just see that the dominant poles of this term minus 8.14 plus 15.9. This satisfied the R condition. Okay, and so the selected values can be written as the what? These terms. This must be equal to 5.43, right? Because we can check the another time. Just one more time check this value. I'm sorry. This is equals to okay, 5.35. 5.35. Okay. So this is the PD. This is the PD, and this is the PD, and this is the PD, and this is the PD. Okay. So we can run 1 second in here. Okay. And then the grid and characteristics, the peak response in here is the 31. It's admittable for our cases, but we need to set the rise time in here, in just like this one, 0.08 in here, because in the previous case we have the 0.3, but in that time the rise time, the peak time, is equals to what? This one, the peak. And also given in here, this is the rise time, this is the peak time. The peak time is equals to what? The 0.18 in that coefficients. Okay, just remember that the peak deviation is given in here, just like this one, but the our objective is that is what is the 2/3 of this time, right? And 2/3 of this time is equals to the what? 2 divided by 3 times 0.3, and so 0.198. In the MATLAB graph, 0.18. It's closing to the each other. It's admittable for this condition. It satisfies the R condition, and so we are correct up to now. Okay, and so in the step 3, we should add I controller. Just remember the design of the I controller. We possess the closest to the origin to this controller, like GPI S is equals to S plus, that's enough to what? 0.5 divided by S. This is the PI controller, because we need to add some pole in here, but we need to add also the what, the zero term in here, to what, to express the effect of the angle. This is the positive angle, this is the negative angle, and so this expressed to the other one in here. And so 0.5 is closing to the what, to the origin in here. Okay, and so if we have this information, and then we turn into the what, again the root locus. Okay, so for the PI controller, we need to copy up the whole of these things in here, just like this one. And so we need to comment the whole the terms in here and PID. Okay, first of all, we need to give the what, the PID parameters in here, and I, and so -8 minus 50.92 and minus 0.5. Okay, and also we need to add the 0 value because the PI controller is equals to what? S plus 0 minus 0.5, and also we need to add the 1 origin term, origin pole, like the 0. Okay, and so PID and PID and PID and PID and also PID and also PID. Okay, if we rerun this code and then we need to select the new poles in here, just like this one. We need to closing the intersection point of the zeta and our root locus, and then we can select that our poles at the at the 4.61, and the poles is equals to this one, but the overshoot and the damping ratio and another things are collected, are satisfied the R conditions, but the selected a 4.61. okay, 4.61 should be given in here. 4.61, and so this is the PID, the PID, the PID, the PID. Okay, great. Oh, okay. And so for the PID controller design, we have the output signal just like this one. First of all, the peak response is equals to the overshoot 14.2, but the second, the T peak time 0.19. This is equals to the 2/3 time of the uncompensated system. There are 2 of them is satisfied at this condition in here, but the steady state error must also be contained in here. Final value is 1, but the 1 second is not enough for these terms. Okay, and so if I run this code at the 4 times and then see that the setting time or the 10 seconds can be given in here, just like this one. Okay, and so we closing to the 0 state error, but with the characteristics of the this form, overshoot not over the 20%, and the peak time is the 0.2, closing the 2, and then we can say that our PID controller is run at this time. Okay, so for the PI controller, maybe we can change the code just like this one, 0.5, for example. But what is change in the system now? And so if I run this code and then we will select the new K values in here, just like this one, 5.26. okay, 5.26. and so if I rerun this code and then just remember that if I add this parameter, and so steady state time is longer than the another ones, right? Okay, and so this the hardest condition for our data. And so if I push to our system is equals to 0.1 in here, it's closing to origin, but we can set these values in here just like this one. And so if I rerun this code for the PI parameters, and then the new coefficients must be given in here, 5.19. okay, 5.19. and so if I rerun this code and then we will get to the to this time says 10 seconds is going to are parameters in here, right? And so if I choose to increase the values of up to this is the normal condition is the minus 0.5, and so if I put the minus 1 values or the minus 2 values for the PI controller, and then if I rerun this code And then we need to select the new coefficients of the k. Just see that I iterate my solution based on this information. I can design the anyway in here. And so the gain must be equals to what? The 3 in here. Okay, and so if I choose the 3, and then if we rerun this code, and then we will have to what? See that at the 2 seconds we'll reach to what? To our steady state condition. This is desirable in here. And the characteristics of the peak response is given into what? With this term. But the peak time is increased in here. Okay? Just remember that. We need to optimize the R system based on this information. We need to iterate the R algorithm to what? To satisfy the T-peak, steady state error, and the other things in here. Okay? And so this is an optimization technique for the PID design controller in here. Just remember that. This is important. So we don't have any exact solution for this kind of systems, but we can iterate the R system to what? To satisfy or to generate the R performance or desired performance to what? To design the R PID controllers in here, just like this one. Okay? So at the step 4 we have the coefficients in here, just like this one, but which one of them is equals to the Kp, Kd, and Ki? We must know that. Now we have the what? The G PID controller. S is equals to what? The K times S plus 5592 times S plus 0.5, right? This is the normal condition, and S. And so 4.6 times S plus 5592 times S plus 0.5 divided by the S, right? Where is it coming from, this 4.6? This 4.6 coming from the what? These terms, right? 0.5 and 4.6. Okay, if I run this code for the 2 seconds, the steady state error going to what? Going to 0. The final value is 1, and the peak characteristics is the what? Is the R desired T peak response. Okay. So these are the equations, and then we can set all the parameters in here, just like the what? The S square form. We can multiply this S plus 1, S plus these terms, and then we will have the what? The 4.6 times S square plus 5642 S plus 27.96. This is the multiplication of these two parentheses. Okay. And S. And also just remember that R, the PID form, is equals to what? The KD times S square plus 5642 S. Sorry. This equals to what? The KP divided by KD S plus KI divided by KD divided by S. And so we can say that the KD is equals to the what? The 4.6. Okay. KP is coming from this calculation, which is equals to this one, and so 259.5. Okay. And Ki is coming from the calculation of this term, is equals to the 27. Okay. 128.6. Okay. Okay. These are the KD, KP, and Ki coefficients coming from the what? The root locus. Okay. So in the step 5, for our open loop transfer function, GS is equals to what? s plus 8 divided by s plus 3, s plus 6, s plus 10. Okay. And also we know that the ts is equals to what? The g c times g plus 1 g times g, and so the r final transfer function ggs is calculated from the what? From the denominations in here. Okay, and so this is equals to the what? These terms kd times s over 3 plus 8kd plus kp s square plus ki plus 8kp s plus 8ki, right? And s over 4 plus kd plus 19 s over 3 plus 8 kd plus kp plus 180 times s square plus ki plus 8 kp plus 108 s plus 8 ki. Okay, so if you put the kd, kp and ki to this diagram, which is equal to the what? The kd is 4.6, kp is equals to 259.5, and ki is equals to 129.8, and then we can see that this system provides to what? The transient and the steady state response of the r desired roots. Okay. This is simple, just like that. And in the real-time application, the ut, the input signal, is equals to what? The kpa plus kd d e dt plus ki integral term e dt. All the time we fed to what? To our algorithm, to this one with the specific coefficients, and then PID controller is done. Okay, so that's all. This is the PID controller design based on the what? The root locus. But in the lab 3 we have the what? The different design techniques for the pole placement techniques, because we can reach the whole the characteristic equation coefficients, and then we can set the kd, kp, ki to the different values of these terms. But just remember that if you want to design the PID controller based on what? Second order approximation, and then we can utilize the root locus techniques just like done in this lesson. Okay.